So in the previous class, we generated the space vectors for two-level inverters. So there are 8 space vectors are there. So out of that, 6 are active and 2 are zero vectors. So that means that will not produce any output voltage. So where that magnitude is 0, right? So this will be the space vector diagram for the two-level inverter. So this diagram is divided into 6 sectors. This diagram is divided into 6 sectors and forming a hexagon. And it is forming a hexagon, right? So inside this hexagon, so we can inscribe a circle, right? So we can inscribe a circle inside this one. So what is the radius of the circle? So what is the radius of the circle? So what is the radius of this circle? So this, what is the magnitude here from here to here? What is its magnitude? What is its magnitude? So what is the magnitude of each vector, each space vector? What is its magnitude? What is the magnitude of each space vector? Are you listening? What is the magnitude of each space vector? I'm asking.
2 by 3 VD.
2 by 3 VD, right? So this magnitude is 2 by 3 VD. Okay. So now anyone can estimate. So what is the value from here to here? So what is that magnitude? So how to find that magnitude? So for example, if it is touching here, right? So this is also its magnitude, right? So how to calculate this? How to calculate the length of this one or the radius of this circle? So what is the radius of that particular circle? So how much angle it will make here? How much angle it will make here? 30 degrees, right? So you know that this value is 2 by 3 VD and this angle is 30. Right. So now tell me what is the angle here or what is the magnitude here? So what is its magnitude? So will it be 2 by 3? Okay.
By root 3 VD.
2 by 3 VD. So is it cos 30 degrees? Will it be the same? Otherwise, so this angle is 90 degrees, right? So therefore this angle is 60 degrees. So from that also you can find out. So how to find that? If you apply the sine rule, so this is sine, so this magnitude is 2 by 3 VD by sine 90, which is equal to, for example, this is x, if you assume that x by sine 60. Okay, so this entire thing is 1 sine 90 is 1, right? So therefore x equal to 2 by 3 VD sine 60 degrees. What is sine 60? What is sine 60?
0.86.
That is root 3 by 2, right? So what is this value? So VD by root 3. Okay, understood? So how we are generated that? See, this angle is 30, right? So this angle is 90 degrees with respect to this line. So this is perpendicular to this line, right? So therefore this angle is 60. Okay. So this magnitude is 2 by 3 and its opposite angle is 90. So sine 90. So this magnitude, if you assume this is x, so x by sine 60. So x is 2 by 3 VD into sine 60. Understood? So this means the maximum radius of this circle, that means the maximum radius of this circle, for example, here. So this value is equal to Vd by root 3. That value is equal to Vd by root 3. So keep that aside. Right. So now, so we will define our reference voltage. We will define our reference voltage. So this is the reference voltage that we required. Or in other words, so this will be the output voltage. This will be the output voltage of the inverter. Okay. This will be the output voltage of the inverter, right? So one complete revolution of this is rotating in the anti-clockwise direction in this particular case, right? So if one circle is computing, means what is its meaning? So it is generating one modulating cycle, right? So in the subsequent rotation, it will be generate another modulating or another output voltage or another cycle of output voltage. Okay. Right. So we can control the magnitude here by adjusting its magnitude of this V reference. So we can control the frequency by adjusting this omega. So we define omega equal to 2 pi f1. So where f1 is the fundamental frequency of the inverter output voltage, right? So by adjusting its speed, angular speed, so we can control the frequency of the inverter. By adjusting its magnitude, we can control the magnitude of the output voltage. Okay. So now you are aware that, so this V reference is rotating, so, and this is rotating from one sector to other sector, right? So it is rotating from one sector to other sector. So let us assume that this V reference is initially set at reference point, or in other words, it is at sector 1. So this is V reference. So this is at sector 1. Okay. So what we have to do is we need to decompose the circle, so which is created by, for example, this is the waveform. So this is creating one circle, right? So what is our next step? So we need to identify the sample time. In other words, so we need to piecewise linearize this circle. So we need to piecewise linearize this circle. Okay. So here, so where you define the frequency of the inverter, the switching frequency of the inverter. So what we have to do is, this is the path of this V reference vector. So what we have to do is we need to divide this into small portions, right? So we need to divide this into small portions. So assume that each portion is of time period Ts. Each portion is of a time period Ts. In other words, so it is known as sampling time Ts. Right. So when you are implementing in MATLAB or any other real-time simulation, so this sampling time is different from the sampling time of the overall file or overall simulating file or any other file, right? So this is different. This is usually known as sampling time. This circle is sampled into different intervals. For example, if you want to increase the switching, if you want to operate at 2 kHz, right? So how many samples you need to consider? How many samples you need to consider? For example, fundamental frequency is 50 Hz, right? So what is Ts? What is the value of Ts? So 50 is corresponding to that. So that is 0.02, right? So 2000 kilohertz. So what is its corresponding time period? What is its corresponding time period of 2000? So that means this 0.02 seconds. So that is divided into 2000 parts, right? So how much you are getting here? What is the time period you are getting? What is the time period you are getting?
10 microseconds.
10 microseconds. Okay. So if you want to have a frequency of operation of 2 kilohertz, right? So what we have to do, right? So here we need to divide this into, or divide this circle into 2000 parts, divide this circle into 2000 parts, and width of each one, so it is equal to 10 microseconds. So this is how we define the frequency of the inverter, right? All right. So here, so this is each sampling time. So that means it is moving from one sampling to other sampling time. So this movement, so it is actually, it's curvilinear, right? So it is actually curve kind of thing. So but we assume that, so this is a straight line. So it is safe to assume that it's straight line because its value is in the order of a few microseconds, right? So therefore we can assume that, so this is, instead of it varying as a curve, right? So we assume that, so that is a straight line. That variation is a straight line. And we treat that as one sample period, and that means sample period, and we assume that, so that entire thing is pointing to a single point, right? The thing is pointing to a single point. That means the vector is pointing to a single point here, right? In the next step, if it is a previous step, so this vector is locating somewhere here. In the next step, this vector is locating somewhere here, right? So we will not consider, or we will not consider the change in the voltage. So when it is moving from, so this point to this point, when it is moving in the during the TS value, so whatever the voltage change is there, right? There is a minimal change in the voltage, so that we will neglect, right? So this is how we sample the path of the reference vector. So this path is circular, or this circle. So the circle is divided into several samples, and we assume that each sample, the voltage magnitude is remain same. So let us assume that this is falling in the sector. Let us assume that this is falling in the sector 1. So this is your reference vector. So this is V reference. We have some, this is your TS period. Okay. So and we assume that this variation is very small. Right? This variation is neglected in otherwise. Okay. So for this, what we had calculated, that we need to calculate the volt seconds. So this vector, our objective is to realize this vector. So this is the vector, right? Our objective is to realize this vector by using its nearest vectors, right? So here in the sector 1, its nearest vectors are V1 and V2. It's V1 and V2, so we need to realize this vector. Okay. So for that, what we are doing is that we need to turn on, or in other words, if you continuously turn on V1, so what is this corresponding switches for V1? So V1 vector, what are the switches we need to turn on? What is the switch state? This is P00, right? So P00, so that's corresponding switches. So that means S1, S6, and S2. So what you observe that if you turn on S1, S2, and S6, the voltage magnitude is this much. Okay, the voltage magnitude is this much. Similarly, so this is corresponding to V2, so that is PP0. So PP0 means 1, 3, so that means S1, S3, and S2 are on. If S1, S2, and S3 are on, so you will get a voltage which is equal to, so this much of magnitude with the appropriate angle. Okay. So but you require this voltage. So what we have to do is we need to modulate this one. So portion of this one will turn on V1, and another portion of this one will turn on V2, so that the output of the overall output, so it will be some intermediate, right? So some portion of switches will on this one for some period of time, and we will on this one for some period of time, so that the output will be, it will be hanging somewhere in between, right? So the output will be hanging somewhere in between this V1 and V2 vectors. Okay. So we have another one, so which is the zero vectors. So there is no role of this zero vectors, right? So because it is producing zero voltage. Okay. The thing is that this zero voltage, or this zero vectors, so which is having states PP0 or 000. So this can be effectively utilized to reduce the switching losses. This can be effectively utilized to reduce the switching losses or reduce the voltage transitions, right? So how exactly we are utilizing that? So that we will discuss later. Thing is that by using this nearest vectors, this V1 vector, V0 vector, and V2 vector, so we can obtain the intermediate voltage vectors, right? For example, if this is the intermediate voltage vectors, so we need to find some ratio of this V1 we need to turn on and some ratio of this V2 we need to turn on, so that the resultant vector will be somewhere here. Okay. So what we have to do is how much time we need to turn on each vector. So that means we have the TS time is there, right? So this TS time we divide it into 3 parts. So theoretically only 2 parts are enough. So that means V1, V2 are enough, right? So, but to reduce the switching losses and other advantages, so we are also considering this V0. So that means, so this V1 vector, so which is on for TA period of time, and this V2 vector is on for TB period of time, and this V0 vector is on for T0 period of time. All right. Okay. So this is TS. So the time TS is divided into 3 parts. So here, so what we have to do that, so we need to find out, so how much time exactly we need to turn on, right? So therefore you require this volt second balance. You might have studied when you study the DC-DC converters. What is its volt second for this V reference? So this is V reference into TS, V reference into TS. So this TA is corresponding to V1. So V1 vector into TA plus V2 vector into TB plus V0 vector into T0. Understood? So we have another equation, this TS equal to TA plus TB plus T0. So we know this V reference, so which is equal to V reference e to the power of j theta. So this is the theta angle, right? And V1 vector, so what is V1 vector? So it is 2 by 3 Vd e to the power of j0. And V2 vector, so it is 2 by 3 Vd e to the power of j pi by 3. And V0 vector, so its value is 0. So V0 vector and its value is 0. All right. So what is the next step? So we need to substitute here V1, V2 and V0 here and separate the real and imaginary terms. And we need to separate the real and imaginary terms. So if we do that, V reference cos theta into TS. So that is the real term of this one. Okay, V reference cos theta into TS. So this e to the power of j theta can be written as cos theta plus j theta, right? Similarly, this is V reference sine theta into TS. Right. On the left hand side, you have, so this is TA into V1. So that means 2 by 3 Vd. Okay, 2 by 3 Vd into cos 0. So that is 1. Cos 0, it is 1 into TA. So this term, so VT is 2 by 3 Vd into cos pi by 3. 2 by 3 Vd into cos pi by 3. What is cos pi by 3? What is cos pi by 3?
1
2 by
by
3 Vd into cos pi by 3. So that is 1 by 2. So that means how much you are getting? 1 by 3 Vd TA, right? Agree? TB. Similarly, on this side, so that means J terms. So this one is T V1, so that is 2 by 3 Vd into sine 0. Sine 0 is 0. Okay, that means there is 0 here. Plus 2 by 3 Vd into sine pi by 3. So what is 2 by 3 Vd? What is sine pi by 3? Sine pi by 3 is root 2, right? Into root 2 root 3 by 2 TB. So this overall thing is 1 by root 3, just check it out if I'm wrong. So VD into TB. All right. So this is the relation we obtained. So V reference cos theta Ts equal to 2 by 3 VD TA plus 1 by 3 VD into TB. So V reference sin theta Ts equal to 1 by root 3 VD into TB. Okay. So we have another one. So this Ts equal to TA plus TB plus T0. So by using these three things, if you solve for TA, TB and T0, right? So you'll get something like this. So root 3 TS V reference by VD sine pi by 3 theta. Another one is root 3 TS V reference by VD sine theta. And this is Ts equal to Ts minus Ta minus Tb. So these are the values of Ta, Tb and T0. So these are the values of Ta, Tb and T0. So what you understand from calculating this Ta, Tb, T0, so what is its real significance? So that means you have Ts period of time there, right? So during the Ts period of time, so we need to turn on this V1 vector, right? So V1 vector, so what are the corresponding switches for V1 vector? That's P00, right? So P00, so we need to turn on this for Ta period of time. For example, if you have 1 second is there, if Ta is 0.3 seconds and Tb is 0.4 seconds and T0 is obviously 0.3 seconds, right? So that means this Ta is on for, or in other words, the V1 vector is on for 0.3 seconds and this Tb is on for 0.4 seconds and this T0 which is on for 0.3 seconds. So therefore, if you done that, so you will get a voltage vector which is equal to this value and this angle is theta. So we can produce a voltage vector so which is having the theta angle and its magnitude is equal to V reference. Right. Similarly, these are for, so this Ta, Tb, Tc, T0 are for sector 1. These are for sector 1. In other words, this theta, it must be 0 less than pi by 3. So these are for sector 1. Right. Similarly, what we have to do is we need to find it for other sectors also. In the same way, you need to find the, for other sectors also, we need to find for TA, sector 2, 3, 4, 5, 6, likewise. So you need to find the TA, TB, T0 values for other sectors. So more or less this magnitudes remain same. So only thing that, so this angle will change. Whatever the sine theta minus pi by 3 is there, right? So this angle will change for the remaining sectors. So now, if you divide this into two parts, right, this angle is corresponding to 30 degrees. So this green one is corresponding to 30 degrees, right? Because this overall angle is 60 degrees. All right. So now which vector is influencing more? So that what we want to study this. So this is helpful. So when you are going for higher levels, right? For example, right, if the voltage vector, the overall voltage vector is falls in this group, so that in 0 to 30 group. Or so there is another scenario, so where that resultant vector or the V reference will falls in 30 to 60 degrees group. All right. So which is dominating here? If this is the one, right? If this is the one, so this is inclined to V1 side, right? So therefore this TA will be more when compared to this TB. That means we need to turn on this V1 vector for more period of time when compared to TB. Similarly, if the reference vector is false in 30 to 60 degrees angle, so in that case, this vector we need to turn on for more period of time. That means TB is greater than TA here. Understood? Okay. So there is another one. If it is exactly here, if the reference vector is exactly here, so what is the value of TB? If it is exactly here, what is the value of TB?
0.
0, right? So no need to turn on the TB vector. So if it is exactly here, so the value of TA is 0. All right. So TB is having some finite value, but the TA value is 0. So there is another one. If it is exactly in the middle of this one, the middle of this angle, so it is exactly 30 degrees. It is exactly 30 degrees. So what is the fate of TA and TB? So obviously it is symmetrical, right? So that means TA equal to TB. TA equal to TB. You can also cross check here, right? If it is pi by 6, so one side you have sine pi by 3 minus pi by 6. This angle is corresponding to pi by 6, right? Sine pi by 3 minus pi by 6, so that is sine pi by 6. And this is also sine pi by 6. So therefore TA, TB, so both are same. Understood? So if it is exactly at this center, right? So we can edit this Q. So we can safely assume that TA equal to TB, which is equal to TC, T0, TA, TB, T0. So all these three values are 0 for that particular case. Okay. So this is about the dwell times and calculations. The same thing it is summarized here. Same thing. So it is summarized here. Right. So next thing is, so you are aware that so everything in an inverter, so we are controlling the magnitude with a modulation index. We'll control with a modulation index. So in case of sine PWM technique, the definition of modulation technique is modulation index, amplitude modulation index is simple, right? So there is a peak value of modulating signal by peak value of carrier signal. So this carrier signal usually vary from +1 to -1. So therefore its peak value is 1. So whereas this modulating signal, right? So if it is less than 1, it is under modulation. So above 1, it is known as over modulation. So those things we already discussed, right? In the same way, so how we will define modulation index of this space vector modulation technique. So if you notice that in this case, particular case, so whatever the, so how, what is the maximum voltage, right? So what is the maximum voltage that can be obtained with this? What is the maximum voltage that can be obtained? So with this, so what is the maximum voltage? So one can obtain, so by using this space vector SVM technique. If you notice that, so we can draw a circle here by joining all the So this is the maximum radius of the circle. So this is corresponding to, so this is the corresponding to, so maximum voltage, so that can be generated by the inverter, right? If we exclude this one, right? If we extend this one, for example, if it is extended somewhere here, right? So what kind of operation it will produce? What kind of operation it is?
Over modulation.
What kind of operation it is? See here, so we cannot represent so each vector. So how much this vector is stopped only here, right? So that means we cannot extend this one. So how much magnitude it is there, right? So that means it is not at all producing any intersecting points, right? So this is known as square wave operation. So the maximum output voltage, so one can be obtained. So that is up to here only. Right. So what is the maximum voltage one can obtain? What is the maximum line voltage one can obtain? What is the maximum RMS value of the line voltage we can obtain? So ultimately, this is obtained from 180-degree mode of operation, right? So what is the maximum voltage one can obtain? So that is 0.78 VD. Agree? This is the value, right? Okay. So that means here, if it is operating at these edges, so the inverter is operating like this. So each one is 120 degrees. So this is similar to 180-degree mode of operation. So this is the maximum voltage. So we can obtain from the inverter, right? So once it is increased, right, even this V reference increased beyond this point, right? So there is no change. So that means it is in saturation. Even though you are increasing the V reference value beyond this point or beyond this 2/3 VD, okay? So there is no change in the output because it is not producing any intersecting points or it cannot realize the vectors. Understood? So now, we can, if you observe that, if from here to so the inside this circle, so inside this circle, so this inner circle, so this will be the linear range up to this point. So this will be the linear range. So that will be the linear range. So from here to here, so there is, so what is this? What is its radius? What is the radius of that circle? What is the radius of this circle? Just now we
Root 3.
calculated, right? What is the radius of this circle?
VD by root 3.
VD by root 3. So from 0 to VD by root 3, so that is linear range. From VD by root 3 to, so this point, so this is 2 VD by 3, so which is non-linear range. From greater than 2 VD by 3 onwards, so that is square wave operation. Understood? So why exactly it is non-linear range? For example, it is operating somewhere here. Okay. So here, so there is some intersecting points. So but whereas here, so there is no intersecting points here. So that means the reference is coming out. For example, if this is the case, the reference is coming out, right? So the reference is coming out of the hexagon. The reference is trying to coming out of this hexagon. So therefore, so that means you cannot build a linear relationship with that. So therefore, it will be in non-linear range from 0 to VD by 3, right? So that's linear range, some VD by root 3 to 2 VD by 3. So that is the non-linear range from beyond that point. So that is operating in a square wave. So with 0.78 VD. So that is the magnitude. So one can obtain. That's the maximum value. So now the question is, so how to define this modulation or how to define this MA? So how to define this MA? So we already calculated that what is TA value, what is TA? So it is root 3 VD TS V reference by VD sine pi by 3 minus theta, and TB is root 3 TS V reference by VD sine theta. So if you notice that if you bring this TS in the other side, it will be TS into V is TS into root 3, right? So TS into root 3, so V reference VD. TS into root 3 V reference VD. Similarly, this is also TS into root 3 V reference VD. Okay. So from this, so we can define the modulation index. So that means this is the peak value of voltage, so that can be obtained. So therefore, we can define this MA, which is equal to root 3 V reference by VD. So MA can be defined as root 3 V reference by VD. Right. So this is how we will define this MA. So this is the maximum voltage so one can obtain, or this is up to that point, right? So this is defined. This now it will become TA equal to TS into MA sine pi by 3 minus theta, and this TB is TS into MA sine theta. So this MA is defined as, from this we define this MA, so this is equal to root 3 V reference VD. So why exactly we define this one, so that we will discuss now, right? So what is the maximum reference V reference maximum value? What is the V reference maximum value in the linear range? What is the maximum value in the linear range? That is corresponding to MA equal to 1, right? If MA equal to 1, okay. So what is V reference? What is V reference? If MA equal to 1, so what is V reference? So
VD by
from
root 3.
this, if MA equal to 1, what is V reference?
By root 3.
VD by root 3, right? Okay. So if you notice that, so this will be the maximum possible, or this will be the maximum, right? So this is the circle, right? This is the radius of this circle, right? So what you understand that, so from 0, so this is the corresponding to the maximum voltage. So this is the maximum voltage obtained in the linear range. So that's why we defined MA equal to root 3 V reference by VD. So V reference equal to VD by root 3. In other words, this will be the maximum voltage. So that can be obtained by using a sine PW space vector modulation. So without going into nonlinear range. All right. So the same value obtained, right? So this VD by root 3. So that will be the maximum radius of that inscribed circle. So modulation range, so it is always vary from MA 0 to 1 range, plus or minus both sides it is there. So now, so how to define the maximum? In one of the class we discussed it, right? Maximum fundamental line RMS value. What is the maximum fundamental line voltage RMS value? So what is the maximum phase voltage value? What is the maximum phase voltage value? What is the phase voltage VRMS value? So this is phase voltage RMS value, right? So this VD by 3. Understand? So this is VD by 3. So that is the maximum voltage. So that can be obtained from the phase. So this VD by root 3. Since we are talking about, so this is the maximum voltage, right? So maximum fundamental RMS value. So this is the maximum phase voltage peak value. So that can be obtained. So this is the peak value. So that is obtained. Understood? So this is the radius of the circle, right? So that is the peak value or the peak maximum phase voltage. So from this, so VD by root 3 into its line voltage means we have root 3 again, and its RMS value, so that is root 2. Understood? So now you obtain, so VD by root 2, so which is equal to 0.707 VD. This is clear? The maximum or the peak phase voltage is VD by root 3. Okay. Peak phase voltage is VD by root 3, and its peak line voltage is into root 3, and its RMS value is by root 2. So that will be VD by root 2. So this is 0.707 VD. If you compare with sine PWM technique, so this is corresponding to MA equal to 1, right? Since we calculate this one, this is corresponding to MA equal to 1. Sine PWM technique. So what is the maximum line voltage we can obtain? What is the maximum line voltage we can obtain with sine PWM technique? So that is 0.612 VD, right? You remember that. With sine PWM technique, so we can obtain a voltage corresponding to maximum voltage is 61.2%. By using overmodulation, right? By using overmodulation, so we can increase its value by 0.70 times VD by using SPWM with overmodulation. Or in other words, SPWM with zero sequence injection. So without going into linear range. So we can increase that by injecting some zero sequence. We can boost the voltage of this DC if RMS value voltage, like this much. So here, thing is that the same value you are obtaining, so without injecting zero sequence harmonics. So without injecting zero sequence harmonics, so we can increase the utilization of DC voltage. Thing is that if you use SPWM, 1000 volts DC, you can get a voltage of 6112 volts. If you use SPM, right, so you can get 607 volts. So that is the difference. Okay. So how much voltage it is boosted? So that means 0.612 divided by 0.707 percentage. Okay. So it will be so how much voltage it is increased, right? 0.707 divided by 0.612. So it will be 15.6% extra. Okay. It will be 15.6%. So what you notice that by using space vector modulation, the DC bus or the DC voltage can be utilized by 15.6%. So when compared to sine PWM technique, in sine PWM technique, to achieve the same 70.7% of the DC bus voltage utilization, so what we have to do is we need to inject some zero sequence harmonics. So we can inject some zero sequence harmonics. So that means, so we are avoiding that. So without adding zero sequence harmonics, we can straight away increase the DC voltage utilization by 70.7%. Okay. So that is the one of the advantage with space vector modulation. So that is not the one advantage. So we have other advantages also there. So that we will discuss in the next class. right? So this is how we will define, or how we will define the modulation index. So there is some confusion if you're going when you're studying some research papers. So there will be some confusion about the modulation index definition. Okay? Someone may use MA, and some papers may use capital MA. So what is its meaning is, right? So what is the meaning is, so we have that standard voltage 78% or 0.78 times VD is there, right? Okay. So in this MA, capital MA notation, so they assume that capital MA equal to 1. So this is corresponding to 0.78 times VD. So whereas small MA definition says this MA equal to 1, so this is corresponding to 0.612 VD. Okay. So that is the usual definition, or sometimes it will confuse you. So there is another definition for modulation index capital MA, that means square wave operation itself, right? So they denote it, so that is the maximum possible modulation index. So better is always, it is better to use this notation to avoid any further confusion. Okay. So MA equal to less than 1, so that is linear range. So MA greater than 1 onwards, it will be non-linear range. So in this case, right, so again for MA, somewhere around I think 0.866 or something, somewhere around, so it's a non-linear range starts from. So that is exactly for MA 0.02 708.784, so that is a linear range. So from 0.784 to 1, so that is non-linear range. So how we obtain this one is 0.784. So this will be 0.612 divided by 0.78. So that will be 0.784. So that is the definition of capital MA. In most of the books or some textbooks, they prefer to use. So just forget this one. So we have to use only the small MA. This is the notation. So any questions?